Welcome to an in-depth exploration of one of culinary science's most fascinating phenomena, the Hollandaise emulsion stability puzzle. Hollandaise sauce represents a triumph over nature's tendency to keep oil and water separate, creating a stable, luxurious emulsion through molecular engineering. Let's begin by understanding the fundamental paradox at the heart of Hollandaise sauce. We know from everyday experience that oil and water don't mix. They're immiscible, meaning they naturally separate into distinct layers. When you pour oil into water, they quickly separate into two distinct phases with a clear interface between them. Yet somehow, Hollandaise sauce contains approximately 80% fat dispersed in only 20% water, forming a stable, homogeneous mixture. The composition is roughly 80% fat and 20% water, creating what we call a high internal phase emulsion. The question becomes, how does this thermodynamically unfavorable state remain stable for minutes or even hours? To understand emulsion stability, we must first examine surface tension and interfacial energy. Surface tension gamma is defined as energy per unit area at an interface between two immiscible phases. For a typical oil-water interface, the surface tension is approximately 50 millinewtons per meter. The total interfacial energy equals surface tension times the total interfacial area. When we disperse oil into small droplets, we dramatically increase the total surface area, which increases the system's free energy. Here's an important question. Why do emulsions spontaneously break down if left unstabilized? The answer is that the system naturally minimizes its free energy by reducing the total interfacial area through droplet coalescence. This is where emulsifiers come in, acting as molecular bodyguards for our fat droplets. Emulsifiers are amphiphilic molecules, meaning they have both hydrophilic water-loving and hydrophobic fat-loving parts. A typical emulsifier molecule has a hydrophilic head that loves water and a long hydrophobic tail that prefers to be in fat. These molecules position themselves at the oil-water interface, with their heads in water and tails in oil. By occupying the interface, emulsifiers reduce the interfacial tension, making droplet formation energetically more favorable. Now let's examine lecithin, the key emulsifier in egg yolks that makes Hollandaise possible. Lecithin is a phospholipid found abundantly in egg yolks, comprising about 10% of the yolk's dry weight. A lecithin molecule has a charged choline phosphate head group and two long fatty acid tail chains, making it highly amphiphilic. Lecithin has a hydrophilic lipophilic balance, or HLB value, of approximately 4 to 6, making it ideal for oil and water emulsions. A single egg yolk contains approximately 1.5 grams of lecithin, which is enough to stabilize enormous amounts of fat. This raises an interesting question. How much interfacial surface area can 1.5 grams of lecithin actually stabilize? Let's calculate the theoretical stabilization capacity of lecithin in Hollandaise. Each lecithin molecule occupies approximately 0.7 square nanometers at an interface. The number of molecules equals mass divided by molecular weight times Avogadro's number. Lecithin has a molecular weight of approximately 760 grams per mole. This gives us approximately 1.2 times 10 to the 21st molecules in one egg yolk. The total interfacial area these molecules can cover is approximately 840 square meters, roughly 2 tennis courts. So the answer to our earlier question is yes, one egg yolk contains enough lecithin for massive emulsification capacity. The stability of Hollandaise depends critically on the size distribution of fat droplets. In a well-made Hollandaise sauce, fat droplets typically range from 2 to 10 micrometers in diameter. The droplet size distribution typically follows a log normal distribution centered around 3 to 5 micrometers. For a given volume fraction phi of dispersed phase, the interfacial area per unit volume equals 6 phi divided by droplet diameter d. Smaller droplets create much more interfacial area that needs to be stabilized by emulsifier molecules. Let's examine how lecithin molecules organize into micelles at the droplet surface. Lecithin molecules form a tightly packed monolayer at the oil-water interface surrounding each fat droplet. The hydrophobic tails point inward toward the fat, while the hydrophilic heads face outward into the aqueous phase. The surface coverage gamma equals approximately 1.4 times 10 to the 18th molecules per square meter. This creates a protective interfacial film that prevents droplets from coalescing when they collide. Lecithin provides not just physical, but also electrostatic stabilization of the emulsion. The phosphate choline head group of lecithin is zwitterionic, meaning it carries both positive and negative charges. This creates a zeta potential at the droplet surface of approximately -30 to -60 millivolts. This negative surface charge creates electrostatic repulsion between droplets, preventing them from getting close enough to merge. An astute question arises. What about the Debye screening length in this system? The Debye length depends on the ionic strength of the aqueous phase and is typically 1 to 3 nanometers in Hollandaise. Beyond electrostatics, steric stabilization plays a crucial role in Hollandaise stability. The lecithin monolayer creates a physical barrier that must be overcome for droplets to merge. The steric repulsion potential scales inversely with the square of the separation distance between droplets. When droplets approach, their lecithin layers begin to overlap, creating strong repulsive forces that prevent coalescence. Steric stabilization becomes especially important in high internal phase emulsions like Hollandaise, where droplets are densely packed. The combined electrostatic and van der Waals interactions are described by DLVO theory. The total interaction potential between droplets equals the sum of electrostatic repulsion and van der Waals attraction. The van der Waals attraction scales as negative Hamaker constant times radius divided by 12 times separation distance. The DLVO potential shows electrostatic repulsion dominating at medium distances, creating an energy barrier that stabilizes the emulsion. The energy barrier created by electrostatic repulsion must be overcome by thermal fluctuations for droplets to merge, which is statistically unlikely. Temperature profoundly affects Hollandaise stability through multiple mechanisms. Hollandaise sauce is typically served at 60 to 65 degrees Celsius, which is below the temperature where egg proteins denature. The viscosity of the continuous phase follows an Arrhenius-type temperature dependence. As temperature increases, the viscosity of the continuous phase decreases exponentially, affecting emulsion stability. Higher temperatures increase molecular kinetic energy, which can help droplets overcome the DLVO energy barrier. However, increased temperature also increases Brownian motion, which prevents gravitational settling of droplets. Let's examine the gravitational effects that can destabilize emulsions over time. The Stokes settling velocity depends on droplet radius squared, density difference, and inverse viscosity. For Hollandaise, the density difference between butterfat and water is approximately 80 kilograms per cubic meter. This gives a creaming velocity of approximately 5 times 10 to the negative 8 meters per second for 3 micrometer droplets. This raises the question, how long would it take for visible creaming to occur? To cream 1 centimeter would take approximately 23 days, which is much longer than Hollandaise is typically kept. A more subtle destabilization mechanism is Ostwald ripening, driven by droplet size differences. Ostwald ripening is a process where larger droplets grow at the expense of smaller ones due to differences in chemical potential. The Laplace pressure inside a droplet equals 2 gamma divided by radius, creating higher pressure in smaller droplets. Fat molecules diffuse through the aqueous phase, from smaller high-pressure droplets to larger low-pressure droplets. The cube of droplet radius grows linearly with time at a rate proportional to diffusion coefficient and solubility. For butterfat and in water, Ostwald ripening is extremely slow because fat has very low solubility in the aqueous phase. The primary failure mode for Hollandaise is droplet coalescence when the protective barriers fail. Coalescence requires 2 steps. Droplets must first collide, then the thin aqueous film between them must rupture. When droplets collide, a thin aqueous film forms between them that must drain before they can merge. The drainage time scales with viscosity times initial film thickness squared divided by surface tension. Lecithin molecules at the interface increase surface viscosity, dramatically slowing film drainage and preventing coalescence. There's a critical volume fraction beyond which emulsion structure changes dramatically. For random close packing of spheres, the maximum volume fraction is approximately 0.64. Hollandaise at 80% fat volume fraction far exceeds this limit, meaning droplets must deform. At high volume fractions, droplets deform into polygonal shapes, creating a foam-like structure with thin aqueous films between them. The elastic modulus scales, with interfacial tension divided by radius times volume fraction squared. This creates the characteristic gel-like consistency of Hollandaise, giving it body and preventing flow. The pH of Hollandaise significantly affects its stability through multiple mechanisms. Typical Hollandaise has a pH between 4.5 and 5.5 due to added lemon juice or vinegar. The isoelectric point of lecithin is approximately 6.5, meaning it's near neutral in Hollandaise. The zeta potential becomes more negative as pH increases above the isoelectric point, enhancing electrostatic stabilization. The acidic pH also slows the denaturation of egg yolk proteins, extending the temperature stability window. When Hollandaise breaks, understanding the failure mechanism helps us fix it. Common causes of broken Hollandaise include overheating, which denatures proteins, insufficient emulsifier coverage, or excessive mechanical stress. When the sauce breaks, you see clear phase separation with large fat globules floating in an aqueous layer. An important practical question: can broken Hollandaise be rescued? Yes, you can rescue broken Hollandaise by slowly whisking it into a fresh egg yolk, which provides new emulsifier molecules. Understanding the distinction between thermodynamic and kinetic stability is crucial. Hollandaise is thermodynamically unstable, meaning that phase separation is the energetically favored state. The free energy of mixing is positive, indicating the mixed state has higher energy than separated phases. However, it's kinetically stable because there's a large activation energy barrier preventing rapid breakdown. The energy landscape shows a metastable emulsion state, separated from the global minimum of phase separation by a significant barrier. In conclusion, Hollandaise sauce is a fascinating and complex system. The stability of Hollandaise depends on multiple factors, including emulsifiers, pH, temperature, and mechanical stress. Understanding these factors is crucial for making a great Hollandaise sauce that is both delicious and stable. By mastering the art of emulsification and understanding the science behind Hollandaise, you'll be able to create a truly exceptional culinary experience.